Welcome to CH225 course on Statistical Data Analysis for Chemists. I am your instructor, Anil Kumar. These are my contact details. This is video 33 in this series. In this video, we will learn the process of hypothesis testing and its application in testing the hypothesis about the population mean. As discussed in the previous video, the first step in hypothesis testing is to define the null hypothesis. Alternate hypothesis is defined as H1. The null hypothesis will be rejected or accepted based on the sample data. Decision will be based on a test statistic called TS. We use sample data to calculate the value of test statistic. We define a region called critical region, denoted as C. If the value of test statistic falls in this critical region, we reject the null hypothesis. Let us take a specific example of hypothesis testing of population mean to understand these terms. We have learned how to predict population mean using distribution of sampling mean. I am sure you remember this picture as well as this expression. This was the expression used for the prediction of population mean from the sample mean for a given significance level when population standard deviation was known. Here, alpha is the significance level. The statistic used was Z distribution. Now, in context of hypothesis testing, the population mean will be known as null hypothesis. Sample mean can be calculated from sample data. The test statistic will be the Z statistic, as shown here, and can be calculated as all the parameters are known. We use the positive value of the Z statistic, as the distribution is symmetrical. The critical region for rejection of null hypothesis will be alpha by 2. If the test statistic falls in this region, reject, or otherwise, accept. Let us do this question based on what we have just learned. Pause the video, read the question couple of times to get a clear idea of how to proceed. Here, the null hypothesis is that the signal intensity is 10. Therefore, the alternate hypothesis is it is not equal to 10. Population standard deviation is known, therefore, we will use Z distribution as test statistic. The significance level is 5%, therefore, the critical region will be a value of Z, which has 2.5% area above it. We can use Z table to find this value, and it comes out to be 1.96. Therefore, if our test statistic is above this value, we reject null hypothesis. We can calculate the test statistic, and it comes out to be 1.79. The test statistic is not in the critical region, therefore, we cannot reject the null hypothesis. Therefore, the conclusion is to accept the null hypothesis that the signal intensity is 10 at 5% significance level. In previous example, the null hypothesis was not rejected at 5% significance level. How about if we change the significance level to 10%? In this case, the critical region will be 1.645. Since our test statistic is 1.79, the null hypothesis will be rejected at 10% significance level. Therefore, significance level is very important in hypothesis testing. As we have just learned, the critical region depends upon the significance level and hypothesis testing. However, the test statistic is independent of significance level. Therefore, we need to calculate critical region for different significance level to accept or reject null hypothesis. A more efficient way will be if we define a single value which can answer all questions related to different significance level. This value is called p-value, and we will now learn how to calculate p-value. Remember, this picture of hypothesis testing for a given significance level. The critical regions and the acceptable region for the test statistic are clearly marked here. The expression for the test statistic is also given here. It is important to note that the test statistic here is a z-distribution and therefore has a z-value which is independent of the significance level. Therefore, what we can do is to mark the corresponding z-value of the test statistic on the distribution as shown here. This is different than the marking of the z-values corresponding to the significance level as was done earlier. Now, we calculate the area above this value using z-table. Once we know the area above the test statistic value, the p-value will be twice that of the area. If you note, the p-value is the smallest significance level at which the data lead to the rejection of null hypothesis. Now, let us do the same for our previous example, wherein the test statistic was 1.79. This corresponds to an area of 3.67% above it. Therefore, the p-value will be 7.34. In other words, the data will reject null hypothesis at a significance level higher than 7.34. If you recall, our null hypothesis was rejected at 10% significance level, but not at 5%. This is in confirmation with p-value. Therefore, the concept of p-value is extensively employed in hypothesis testing, as its value does not change with significance level. Please calculate the p-values by assuming the average of 20 signals to be 10.8 and 7.8 in the previous example. Confirm that your values are same, as shown here. As can be seen, lower is the p-value, higher are the chances of rejection of null hypothesis. It is a standard practice to report p-value along with a decision on null hypothesis. P-value provides a measure of the credibility of the null hypothesis. Higher is the p-value, stronger is the evidence that sample data supports the null hypothesis. The p-value is not the probability that the null hypothesis is false, nor is 1 minus p the probability that the null hypothesis is true. The null hypothesis is either true or false. There is no probability associated with this. So the proper interpretation of the p-value is in terms of the risk of wrongly rejecting the null hypothesis. Following are the general guidelines to interpret p-values. A p-value of more than 0.1 indicates a strong support for the null hypothesis or weaker evidence against it. A p-value of approximately 0.05 indicates a borderline case and is considered as a moderate evidence against the null hypothesis. A p-value of less than 0.01 indicates a strong evidence against the null hypothesis.